All right, cool. Everybody doing okay? Happy Thursday so far, or Friday, if Friday is your Thursday. Exams, you guys can collect them after class if we have time, but if not, you can come by my office after lab. So today around probably 10:30 or so, or next week, you know, I'll bring them before class too. Review them if you have any issues or any questions on the point breakdown. If you're like, I thought I did this right, how did I get it wrong? I'd be happy to meet. Just set up an email for tomorrow, or you can come to my office hours next week too. But today we are going to be continuing on with our soil classification. We were covering the USCS, which stands for what? Which stands soil classification system. Yeah, unified soil classification system. Even though that's a mouthful, that's one of the easier acronyms that we're going to be working with, because today we're going to introduce the AASHTO system, which is it's American Association State Highway Transportation Officials. It's okay if you don't know that, because I didn't memorize that until like a few weeks ago. So it's okay. Just know that AASHTO is for roadway. USCS is for structures. So try to keep it memorized that way. So if your client wants you to do a geotech report for a roadway project, they're putting in like a new lane of a highway or a new highway or something, then it would be a AASHTO classification. But if you're doing a structure, so which includes bridges or walls or any type of thing that a roadway might still be on, but if it's a structure, then it'll be for the USCS. So the USCS is based off of a 2-letter symbol, and that is 1 showing the gradation or the grain size, and then 2, if it is a coarse grain soil, then we're talking about a description of the gradation, so well-graded, poorly graded, clay, or silty. Or if it is a fine grain soil, then we look at it in terms of plasticity, level of plasticity. So it's either L for low plasticity, high, or H for high plasticity. And the demarcation zone is just based strictly on the liquid limit, which is a Atterberg limit test, which we'll go over in a few weeks. So it's based strictly on the gradation, plasticity, and organics. So for example, like if we have something like this, an S, N, and M as our group symbol, the majority of the particles are the size of a sand. So that's what that first one is telling us. And then the second one, the fine particles behave like a, what is M? Yeah. So that's physically what we should think of when we see that we have a soil that is a SM, which is a silty sand. So majority is sand, but the particles that are fine behave like a silt. So then like this, a GP, that would mean that the majority of the particles are the size of a, what is it? A gravel. And that P is telling us that the soil is non-plastic, so there is not a majority of material that is fines. So then instead of caring about the fines and whether it's plastic or high plastic or low plastic, that P is telling us that it is poorly graded. So most of the time you're going to be referring to like just the group symbol, but as we said before in last class, we're also looking at the group name, which breaks it down into a little bit more details based off the 15%, whether it is gravel or sands, and you just follow that flow chart. So I've ended on this example. We didn't get a chance to go over it. So this is a good one of how to follow the grain size distribution and classify the soil based strictly on that. So we're asked to find the group symbol and the group name. We're also told that the soil was determined to be non-plastic. So that means like the engineer like held it in his or her hand and determined, okay, there's no plasticity through this. There's also no organic. So it's an inorganic, the organic content is at 0%. So what we would have is our grain size distribution. This is exactly like what we're going to be doing in the lab this week. We have the mass retained. We know the corresponding opening size to each sieve size, and that's important because that's our x-axis. So what we could do is add all of that up. That's supposed to be a sum, and then we can find the individual mass retained or percentage mass retained on each one. This is just, if this one is 1, this is just 1 divided by the sum of all of them. And then the cumulative percent retained is going to be, we add each one. So it's a stepping stone. And eventually we'll get to 100%. So what we need to find is our gravel fraction, our sand fraction, and our fines fraction. From that, we can see that the gravel, it's about 2% gravel. For our sand, it's 94 minus 2, and that is 92%. And then for our fines, it's about 6%. So again, the thing to remember with this is that dividing line between the two. So gravel is greater than number 4 sieve. Sand is in between number 4 and number 200. And then our fine is less than 200 sieve. So fines are sometimes just shown as minus 200, so less than the 200 sieve. All right, so we have all of those informations. We know the soil isn't plastic, so then we can go to our handy dandy massive confusing flow chart. But what we can do is just concentrate on one of these two paths. We know it's not organic, and we know that the majority is fine grained, or sorry, coarse grain. So we know it's not going to be a fine grain because the majority is passing, or the majority is retained on our 200 sieve. All of that stuff goes away, and now we only look at these two paths. Do we have a greater percent mass passing the number 4 sieve or a greater percent pass retained on the number 4 sieve? So what is our percent retained on the number 4 sieve? 2%, yeah, exactly. So obviously we have a greater percentage passing our 200 sieve or our 4 sieve than retained on our 4 sieve. So what we would do is follow this path so we can forget all of that stuff and only look at this little tree now. So we know our soil is going to start with an S, whatever we do. So it's going to be primarily sand. So it's going to start with an S. So then we look at the percent passing the number 200 sieve. That percent passing the 200 sieve is down here. So we're at about 6%. So we are somewhere between 5 and 12%. So that's this column right here. So everything else goes away. But what we need to do still is calculate the CU and CC to determine whether it is an SPSM or an SWSM. So this P and W is either poorly graded or well graded. So to do that, we look at our grain size distribution curve. And remember, from CE materials, we were just looking at it and visualizing it and like determining whether it's well graded or poorly graded. Now we actually have numbers associated with that. So we look at our CU and our CC, which are calculated from our grain size distribution curve. So if we were to calculate these, our D, each one that we need to find our D10, which is here, our D30, and then our D60. So that corresponds to the diameter that is equivalent to that percent passing. So we read where it would intersect on the x-axis because we're looking for the diameter specifically. So this is when we have to kind of eyeball it and guess here, but if our D60 is about 1, 2, 3, 4, or 2, 3, 4, 5, so it should be about 0.5. And then our D10 be somewhere about 0.14. So we'll say that CU is about 3.6. And then for our CC, D30 squared, don't forget that squared there, divided by 0.5, which is our D60 times 0.14, and that's about 0.82. So we know that these are our two values. Our CU is 3.6 and our CC is 0.82. So what we have to do now is see which tree it goes into. Is it going to be well graded or poorly graded? For it to be well graded, that means our CU has to be greater than 6, and our CC needs to be either less than 1, or sorry, no, greater than 1, but less than 3. So for poorly graded though, if our CU is less than 6 or our CC is either greater than 1 or greater or less, sorry, less than 1 or greater than 3, then it would be poorly graded. So this gets kind of confusing, especially this one right here, because what we have to think of it as, if our CC is here, we have 1 and we have 3. This is like the range here. Our poorly graded soil will be out here. So this would be poorly graded if it is well graded, then it'll be in this range. So don't get too mixed up with the, the carets greater than or equal to signs there. We're saying is if it's beyond the scope of 1 to 3, then that CC value represents a poorly graded. So our soil in this case is poorly graded. So that means it is an SPSM. So we have to go back and double check that tree there because we have the OR option. So these little rules right here, this is to determine whether it's poorly graded or well graded for any of the, sands or gravels or anything like that. So we know it's SPSM. So now we need to find the additional name. So we look at our chart. We have SPSM here. We have to see, is it greater than or less than 15% gravel? So we are 2% gravel, which is obviously less than 15, right? So then we go down this route here. We're less than 15% gravel. So what we would call this is a poorly graded sand with silt. So only if it's greater than 15% gravel would we throw like a with gravel in there. So we just keep it as poorly graded sand with silt. Any questions on this one? If it takes some time to go through it again, like it's completely understandable because it's kind of tricky. Yeah.
If this was a question that
yeah. Mm-hmm. All right, so the next one, classify the soil according to the USCS system. And we're just asking to provide the group symbol for this. So we're just given the grain size distribution curve, which is normal sometimes, like your lab tech would just do the test. They'd give you the grain size distribution, and then you'd have to determine the actual gradation or the actual classification based off of that. They also did Atterberg limit tests. So we have our plastic limit test and our liquid limit. So from that, we can calculate our plasticity index. Our plasticity index is our plastic limit minus our liquid limit. And if you remember from that Atterberg chart, that's one of the inputs that we need. So 35 minus 30, so that means our plastic index is 5. So we can also find our percentage gravel, sand, and fines. So for our percent gravel, you have to eyeball it, but if this is the separation here, so this is our number 4 sieve, which is equivalent to 4.75 millimeters. How we would read this is about here. If we have about 98 here, then that means 98% of our material is less than gravel. So that means 2% of our material is gravel. So that would mean 2 for sands. We actually have to do some math by looking at where the fines are. This is our fines here, which is our number 200 sieve. We would read where that intersects. So if we have 98 minus 20, that is 78%, which is our percentage sands. And then everything would just be 20 minus 0, and that would be 20% for our fines. So make sure you're able to read just these types of gradation charts and see like how like each gravel, sand, and silt, or gravel, sand, and fines are distributed along like a chart like this from the x-axis. All right, so we have our plasticity information, we have our gradation information. Now we go to this crazy thing. And if we know that it is 2, 78, and 20, so is a greater amount or greater than 50% passing the 200, or less than 50% passing? So we have 20% passing. So that means the majority is going to be coarse grain. So we start in here. So we only follow this. Now, do we have a greater percent mass retained on the number 4 sieve, or a greater percent mass passing the number 4 sieve? So that's 2 versus 78. So we have a greater percent mass passing the number 4 sieve. Now we go down here. So then are we between, or we look at the number 200 sieve now. Are we less than 5, between 5 and 12, or greater than 12% passing the number 200 sieve? So that's this. Our 200 sieve is our fines. So since we have 20%, we're greater than 12. That means we're in this box. So now we have to look at our liquid limit and our plasticity index. And then we look at our chart. So we know it's either going to be an SP, an SMSC, or an SC. So if we look at our chart, you'll see it only has MLs and CLs and MHs and all that stuff. So if we know the majority of our soil is still sandy, but this is to define the fine behavior. So everything, the rules still stay the same. But instead now, instead of the M's, like basically the way we're reading this is if it is clay up here versus silt down here. So these symbols aren't ML or CL, but now we're looking at SM versus SC. And then this little patch right here, that is our SCSM. Again, that's because the 3 options we have are these: SM, SMSC, or SC. So we still use the chart to determine whether it's a primarily silty behavior or a primarily sandy behavior, or clay behavior. So this line now separates it into just silts or clays. We don't care about the plasticity or the liquid limit. So we had our plasticity index of 5. Make sure you're reading this plasticity index for our y-axis. So if we're at 5, we're somewhere here. Our liquid limit is somewhere here. You can see that would intersect in this area right here. So this would mean that our soil is a what? So that would be a SM. So that would be the group symbol. Yeah.
will always have.
So it depends on where you are in the flow chart. If you're a clay, if you're on this side, you see all these options. These are CLs. This actually uses that chart into the high plasticity, low plasticity. Down here. So with these, the majority of the soil is, oh, well, it'd be still the same. So gravel, the gravel is either going to be clay or silty. So it's either going to be gravel with an M or gravel with a C. So both cases in this, we don't care about the high or low plasticity. We don't care about that line for sands or for gravels. We only look at if it's silty or clay. So that's what that A line is telling us. Anything above the A line is a clay, anything below the A line is a silt. Sorry, I guess this should be SMSC technically. Okay, so the homework that'll be, is it already posted? Okay, I need to double check, but there's a few examples like in this that for practice. Yeah. Yeah, so we were on this flow chart right here. And so since greater than 12% is passing the number 200 sieve, is up here, we have 20% passing the 200 sieve. We follow that tree down and we're either in, so our sandy soil still has enough plasticity in it that needs to be defined. So from that, we still look at the Atterberg plasticity chart, but instead of caring about the OH and the C or the H and the L, we look at just the A line. And we still plot the two values here, the liquid limit and the plasticity index. But now since we know the majority of our soil is going to be sand, this is not going to be an MH, it's going to be an SM. If it was up here, then this would be an SC. Same with this area. This would be an SC or an SM. So that A line that you see right here, this A line is the thing that divides us in between a silt or a clay. And we still have this like little no man's land hatch zone. That is kind of a combination of both. So that would be our SMSC instead. Is that clear? Did anyone, you have a question? Somebody else? Okay, cool. All right, I know if you're not used to following flow charts, then this is probably like, what the heck is going on? But just try to take it slow and realize like that once you are on one tree, then you can forget about the rest, you know, like it's overwhelming if you look at it that way. Or check out the ASTM that I posted too. It's on Canvas. That flow chart might be designed a little bit different and it might be more clear or more intuitive, like just the way that you think. But, yeah.
Different countries that have different flow charts, but are like the categories more or less the same?
So not necessarily different countries. There's just different classification systems. So this is the unified soil classification system. So, anyone who uses this is using this flow chart.
Okay, so it's not just the US.
Right. No. Yeah. I mean, depends who else would. Some other countries might have their own classification system, but this unified soil classification system is trying to become the unified one, which just takes a little while. So like, for example, like the next one that we're covering is the AASHTO classification. So this is based off of a different ASTM. So you'll see a flow chart for this one too, but it's completely different because it's a different like language of determining soils. So it's different. Like the end goal is still going to be very similar where we have like a gravel or a sand or a fine grained soil, but the categories are different. So this one's posted too now. You can download it and you'll see the same things. Just to recap, the main difference between these two, this was the USCS one that we just went over. Now we're going to be going over AASHTO. This one is used for roadways and transportation. Where the structure is including roadway structures, so bridges, included in that. Like even though you're building a structure for a roadway, like you would still use the USCS. The AASHTO is for like general roadway, so like a 500-yard lane, you know, just on the ground. All right, so AASHTO, American Association of State Highway and Transportation Officials. This was developed a long time ago too, so who would have thought? All this stuff is really old. And it was basically when public roads started becoming booming. There's a AASHTO like testing facility, I think in like Illinois or something, or Indiana, one of those states that nobody goes to, that you can go and still see like the historic area where they were first learning how to standardize asphalt and standardize the subgrade of it. They like used to just like have like these cars driving on this track for like days on end just to test the asphalt and the subgrade. Now we have these massive like semi-truck simulators that have a tire going over and over and over again to simulate traffic. But back in the day, they would just drive and waste a bunch of gas and stuff. So it follows these two. The ASTM has their own standard, but then also AASHTO, if you're familiar with them, they have their also testing standards. It's the same thing. So they're just publishing in two different sources. So you can follow either one of those. I generally think the ASTMs are a little bit easier to follow. So that's the one that I like to download and keep on file. So it is based for a classified or soil rating for, we already talked about this, but it's roadway construction, or sorry, roadway subgrade. So if you remember from the CE materials class, we had like different layers of like what we would call asphalt. We would have the actual asphalt layer at the top, right? And this would be pretty thin, but this would be our asphalt concrete. And then underneath that, we might have different layers of aggregate. Something like this. This would be our subbase, so aggregate subbase. And then we would have our layer underneath that, which is either the natural earth or the brought in fill material, and that's our subgrade. So that's what this is meant for. So that's our subgrade. Wow, that yellow sucks. That says subgrade. So what it is classified into is 8 primary groups. Now, some of these groups have these subgroups that we'll talk about in a second. But like the best way to think about this again is that like this is all in the scope of roadway subgrade. So we have this A1 for AASHTO. So A1 would be the best soil to use for roadway subgrade. And then A8 would be the worst case. So it's just a scale like that, except it's 1 through 8 for some weird reason. So A1 is best soil that's used for subgrade, and then A8 is the worst one. So there's these like kind of categories, A1 to A3. There's A4 to A7, and then there's A8. So the categories, instead of talking about like for the USCS where we have gravel, we have sand, and then we have like fines and then organic, it's kind of grouped into 3 main things like this. So A1 through A3 is our granule material, and this is the stuff that is excellent. This is all just for its rating for subgrade construction. A4 through A7, this would be our silty and clay material. So this stuff is fair to pour, so it's still okay. Like we can still make it work and build a road on top of it. Who wants to guess what A8 would be? Can we build something on A8? Yep. Nope. Yeah, so as you'll see in the trend here, organic soils, muck, peat, anything with really high compressibility, really high moisture content, like you don't want to build a roadway on that. So they would actually have to remove it or do some type of ground improvement in that area. So A8s are bad. Now, so for the granule material here, and for the silty clay material, we have some subgroups too, plus several subgroups. So the actual rating that you'll see looks something like this. There are the A and then the primary number, and then you'll have a subgroup number. And then you could also potentially have a group index. So the A1 through whatever, like A1 through A8, that's this gold number here. So that's what was on the previous slide. The subgroup here is not always used, but some soils will have this additional classification, and then that group index is a further classification. So think of it reading from right to, or left to right. So this is telling us how good the soil actually is for subgrade through A1 through A8. But then if there's some like borderline soil, then we add this subgroup. And then if it is a poor soil, then we add this group index for further characterization. So the key differences to look compared for the USCS, because you'll see a lot of the same things. They still use the grain size distribution. They still look at the plasticity. But for USCS, the fine versus granule, like if we had a sand or a gravel versus a clay or a silt, that dividing line was 50% passing the 200. So for this, they only look at 35% passing the 200. So you have much more granule material than, or sorry, you have more options of fine material than granule material. There is no coefficient of uniformity or coefficient of gradation, like from the grain size distribution plot. Instead, they use this group index equation. So that's what this thing is. Instead of, this tells us if it's well graded or poorly graded, basically. And then our plasticity chart looks very similar, but just to be confusing, it's different. So the categories, instead of the high plasticity or low plasticity at 50%, they use 40%, just so they couldn't get in trouble for copying or something. I don't know. So the flow chart looks kind of the same too. I think this one looks a little bit prettier because you can add some colors to it. So that's kind of nice. But remember, A8 is the worst case scenario. The worst case, you don't want to use this for subgrade. Everything on the right-hand side, it gets better as we move from left to right. So I tried to go starburst colors on you guys and help classify this. But same as before, that peat is all based off of visual observation or an organic content test. So that's the first little sub tree off of it. The other two ones determine whether it's silty or clay material or granule material. And if you notice again here, this is 35%. It's not 50%. So USCS was 50%, just majority rules. For this, it's 35%. So you could have 60% of your material being granule or clay material, or sorry, granule material. And no, you could have like, yeah, you could have 70% of your material granule material, but it would still be classified as silty because more than 30, no, other way around. You guys get the idea. There's more, they're more keen to identify something as silty or clay. I can't explain it this early in the morning, but there's a greater chance for this that it's silty or clay because the threshold is less. Instead of 50%, now we're just looking at 35%. So if a smaller chunk, 35 or less, then we call it silty still. Besides that, it's all kind of similar. Right here, These are we look at the plasticity chart actually. The plasticity chart's a little bit easier to look at. There's not like a double boundary. Instead, we have still the plasticity index. I don't know why it's backwards like that. So this is our PI, which is equal to our PL minus our LL, and then our liquid limit here. So if you see the dividing line is right here at LL equals 40%. So anything on this side is technically what we would call consider a high plasticity, and anything on this side is what's considered a low plasticity. So that 40% is just kind of like an arbitrary line again that they developed in the 1930s. If you remember, this is for the USCS, so this is the Atterberg chart. It looks very similar, but our liquid limit here is at 50%. That's the thing that distinguishes between the two. So don't, keep that in mind. Like that liquid limit is an important test that we do on the soils. And when you do the liquid limit in the lab in a couple of weeks, you're probably going to laugh because it's a really dumb test, but it's a really important for classifying soil. So the group index is also added for certain soils. So if soil is A1, A2, or A3, so if it's one of the high quality soils, then we don't worry about the group index. So group index is equal to 0. There's these two other if equations. So if the soil is A26 or A27, then we calculate the GI using this equation, where F is the percent passing 200, the percent fines, and it's in percent form. So if we had 50%, then it'd be 50 minus 15, something like that. So if the soil is anything besides those two, so any of the other poor quality ones, then just to make our lives more difficult, they made this crazy long equation here where you'd plug that into it. And this is a function of the plasticity index and the liquid limit. And everything here is in percent. If you put those in decimal form, then you'll get these crazy negative numbers and it wouldn't make much sense. So in general, what this group index is telling us is as the group index is a lower value, then the quality of the soil used in subgrade is going to be better. So these are the good quality ones, remember? Good to excellent. So GI is 0. These are like the not the best, but we can make it work. And then these are generally the not so good ones. So the GI value will probably get higher as we go. Or yeah, as you continue through it. So there's a few rules. If the GI is, what's going on here? If GI is negative in the first cases, then GI will always go to 0. So you'll never show GI as 0. Generally, you'll calculate, if the GI is negative, then what you're doing is accidentally calculating it for a soil that doesn't need to be calculated, or you are not keeping the variables in percent form. So just double check that. The GI is also always rounded to the nearest whole number, which kind of makes it nice. So you would just round to the nearest one, either round up or round down, depending on what you'd have. There's no technical upper limit for the GI value, but in general, a GI greater than 20 indicates a very poor subgrade. So you'll see some of the state transportation like places like FDOT and maybe like some of the other ones, generally in their codes, they'll tell you that a roadway subgrade cannot have a GI greater than 20. So you'd have to calculate that and make sure if it is greater than 20, then they might make you retest it or remix it or something like that. The GI should also only be used for comparison between soil in the same group. So that means you can only, if you have an A4, then you can only compare the GI values in other A4s. If you have an A5, you can only compare the GI value in other A5s. So the GI value is helpful because let's say you have like a borrow pit or like, you know, a quarry of material. And then this owner's like, hey, I'll let you use this soil for the roadway or the highway that's going in nearby. You would do these tests to determine the GI, and if they're both A4 soils, or if the two different mines or whatever are both A5 soils, then you can compare, calculate the GI value, and then have a quantifiable comparison to determine which one is better. But if one site is an A4 soil and one site is an A5, then obviously you would go with the A4 because it's better suited for it. You wouldn't calculate the GI value and compare them. That's an example there. All right, so let's look at an example here. Classify the soil according to the AASHTO system. There's no indication of organics, and the soil is not plastic, so it's only going to be granule. So for that, we don't need to do a full sieve analysis for AASHTO, which is kind of nice because there's no coefficient of uniformity and there's no coefficient of curvature. So for AASHTO tests, you really only need three things. You need the number 10, the number 40, and then the number 200. So we have this. This is telling us that our silt and clay, remember that dividing line, if it's greater than 35% passing the 200 sieve, then it's going to be on one side. On the other side, it's going to be granule. So we don't actually even need that number 4 sieve. We just say everything is going to be granule on that side. So if it's greater than 35%, then it'd be great, or less than 35. For this, 6 is less than 35. So we know it's going to be a granule material. So that's our first dividing line. So we already knew right off the bat, this isn't going to be it. Since less 35% or less, then we go down this path. Everything else can disappear. Now we just have to ask ourselves questions. So is it less than 25% passing the number 200 sieve? We look at the PI value, and then we look at the number 4 sieve. So for this here, less than 50% passing the number 40 sieve, which makes sense. And then we look at these two like check marks. So what you would look at is if these, like read these as if statements. So if there is less than 50% passing the number 200 sieve, and there is less than 30% passing the number 40 sieve, and there is less than 50% passing the number 10 sieve, and the PI is less than 6. So the PI is less than 6 here. And then this is basically like these criteria. So if it checks all of these boxes, then we can call it an A1A. So then, but if it didn't check all those boxes and only checked these boxes, then we would call it an A1B. So it's an A1A. For the GI, what would the GI be? 0, yippee, yep, yeah. So the actual classification here, we would still put that GI value, so it'd be an A1A0. Because this down here, the soil is either one of these, then we know automatically that that GI is going to be 0. If anyone's colorblind, I'm sorry. I kind of made these like specific to for color. Yeah. Yeah. So normally that it's given right here, but it would be like defined by like the lab tech or somebody. Like you would physically be able to like feel that the soil is just falling apart. So you usually only do the Atterberg test or determine if it's plastic if there's signs of it. Same with organics. Like you wouldn't do the organic test on just any soil. Like if you look at the soil and there's leaves sticking out of it, then you're like, okay, I should probably do the organic test. Same with the Atterberg limits. All right, another example. Classify the soil according to the AASHTO system. No indication of organics was found, but it is plastic because they did Atterberg limit tests on it. So we're told that we have a plastic limit of 49 and a liquid limit of 37. So that means it's going to be, it's behaving like a clay. So we're given a little bit more information here. But again, what we care about is down here. Is it greater than or less than 35% passing the 200 sieve? For this, it's really close, but it's less than 35% passing. So we're still granule material. So we're still hanging out over on this side because it's 34%, not 35. So is it less than 35% passing 200 sieve or less than 25% passing the number 200 sieve? So it's not less than 25% since we have 34%. So that means we go down this route instead. So now what we would look at is the liquid limit or the plasticity index and the liquid limit. So if our PI is greater than 12, or sorry, greater than 11, which is, it is because it's at 12, then we look at these two options. Is the liquid limit greater than or less than 40? So our liquid limit is 37. Our liquid limit is less than 40, which means our group number would be our A24. So these steps right here, like this step, this is just from the chart. But for AASHTO, the plasticity chart's a little bit easier to define. It's not like a weird angle. It's just these two functions here, or it's a straight line. So it's not an equation like the USCS one. So that's why we can just include it in there. But if you were to just look at the Atterberg or the plasticity chart for AASHTO, then all those steps under this line would be the same. Like you could just look at that. So for the group index, we still have to calculate that. So we know it's an A24. We go back to our group index. If it is an A26, then we use this equation here. So our F200 is equal to 34. And then our PI is equal to 12. This would be 12. So we plug that in again, make sure that these guys are still in percent form. And we find a GI of 0.38. So what do we do with this then? What would the GI value actually be? What would we say? Yep, yeah, 0, right? So that means our classification, we still round down, or even though we're getting some GI value, it's still a decent soil. So it's an A260 would be our AASHTO classification. Does anyone think this is easier than the USCS one? Does anyone think it's just all confusing and hard? Yeah, no. Flow charts. It's not fun. All right, one more example. So we're given the sieves analysis, and we're also given the Atterberg limit stuff. This one though, now we have 62% passing our number 200 sieve. That's obviously greater than 35. So we know this is going to be a silt or a clay. So if we look at our chart, it's not this stuff. It's not that. So now we are going straight down the silty clay material. So it's either going to be an A7, an A6, an A5, or an A4. And so we look strictly at the Atterberg chart now. Sorry, not, yeah, the Atterberg tests. So for this, our PI is 12%, 55 minus 43. So our PI is greater than 11%. So that means we follow down here. Is the liquid limit greater than or less than 40? Liquid limit of 43, so it's greater than 41. So now what we would actually need to do is check the plasticity chart to determine if it is an A76 or an A75. So our liquid limit is 43, somewhere in here. our plasticity index is 12, somewhere in here. So it's actually really difficult to discern what side of this line it is on, right? Like unless you have it scaled, it's somewhere, it's either an A76 or an A75. And luckily we know the function of this line. PI is equal to LL minus 30. So what we would do is just plug that in and see if our PI is greater than this value or less than this value. If it's greater than this value, then we know our PI is above the line. If it's less, then it's below. So we have 12 for our PI, 40 minus 30 is 13. So it is less than the actual calculated value. So if it's less than, that means it's below the line. That means it would be an A75. So especially when you get into kind of like the 40 liquid limits and like the sub 20 plasticity index, you may actually need to look at the equation itself to determine where it is above or below. And that's why they give you these equations of the lines. Same for the USCS procedure too. Like they give you the equations for that. Okay, so it is an A75. Can't forget the group index. So with an A75, it's going to be in this anything else category. So we have to calculate that all out. This is our F200, our liquid limit, and then our plasticity index is 12. So keep everything in decimal or percentage form. And we get a GI value of 6.7, which is about 7. So still mildly okay. Like this isn't the end of the world if we get this soil, even though it's a high rated AASHTO, and it is calculates a GI value. Because remember, the GI for subgrade is 20. Like anything greater than 20 is a no-go. So at least 7 is still relatively decent. This would be our classification. Okay, so the key points with the AASHTO, I know it's going to take some time, and I wish there was a better way for me to, effectively teach this, especially at 8 in the morning, like looking at flow charts the whole time. But go over the homework slowly, and don't just rely on Googling stuff. One of the things that actually I think is kind of helpful, that might be like if anyone likes coding or anyone likes MATLAB or Excel. Anybody's that type of person, then setting up setting up some type of code or Excel function where you plug in these values and it follows and produces an SM or whatever. It's a good way of like practically thinking of, because it all is just if statements. Like following a flow chart is if it is this, then this, if not, then this. So whatever, you can try that. But just to recap, remember A1 through A3. This is for granular material. This is our good stuff for subgrade. Like this is the stuff, if you have it at your site and they're building a highway nearby, and you're a farmer and own a bunch of land, then you can make a bunch of money because they're going to need that soil. A4 to A7, fair to poor, still acceptable. But our A8 is nope. Like we cannot use that stuff at all. So for anything in this area, this dividing line is the 35% passing the 200 sieve. So if you're looking at AASHTO, it's 35%. If you are looking at the USCS, this dividing line between granule and fine sand or fine material, that is 50%. So that's like the key difference here. Like, so 50% for USCS, 35% for AASHTO. The silty and clay material, to determine whether it's different, they look at this plasticity chart, which is a little bit different than the USCS one, right? So this is still, the PI is a PI value of 10 is dividing it for clay or silt, where for us, for the USCS, the liquid limit of 50 is high or low, and the PI is a function to determine whether it is clay or silt. So there's similar principles here. It's just, again, they're gearing it towards different audiences. So there's different equations and different classifications, but at the end, we're still looking at the same broad categories of soil: granule, sandy, or silty and clay. So there are some typical comparison charts. Don't worry too much about these. Reference them if you need to, like 30 years from now when you're working. But most of the time, like most projects are going to require you to just go through the testing and then the actual real classification. Not many times will you need to like translate in between these two values, but it still can be kind of helpful, especially if you're working in roadway projects, because the majority of subsurface testing will follow this. But if you're working at a roadway project and you need subgrade fill, then you would have to have AASHTO. So knowing where some locations are for borrow material might be helpful to know that, like, you know, if you have a SP or an SW, then those will most likely be A3 or A1 fees for that, because that's like good